All right, here we go. So we're going to continue our discussion of friction, but this time we're going to have problems in which there are forces that are at an angle to the horizontal. All right. So this is just a quick refresher of how to deal with what happens if there's a force at an angle. The first example here, there's only two examples here. This is going to be a short video. The first example is a review. The second example is going to be new. So please, please, please watch it. Don't just skip to the second example because you got to watch the first one to get to the second one. Here we go. Kabam. Forces vector. All right, so I don't know if you can see here, there's a tiny little lawnmower here. Let's pull them big in the lawnmower. Boop, boop. Oh, no, we won't because it's locked. All right, anyway, there's a lawnmower there. All right. Now, it says the wheels on this 40-kilogram lawnmower are jammed, so Roy has to slide the lawnmower instead of actually rolling. All right, so it tells us that Roy pushes the handle with a force of 90 newtons at 50 degrees below the horizontal. And then it gives us the coefficients of static and kinetic friction, 0.6 and 0.4. We got to make a free body diagram and find the acceleration. All right, so the first thing I'm going to do is I'm going to deal with Roy's force, right? So Roy's force, not to scale, is 90 newtons at an angle of 50 degrees below the horizontal. All right, that force is going to have a horizontal component and a vertical component. All right, and you can do your trigonometry and figure out what those components are. Doing so will give you the horizontal component ends up being let's just call it 57.9 newtons, and the vertical component is 68.9 newtons, negative style. All right. So I think we can now take that information and make our, whoa, that's not at all what I wanted to do. We can take that information and put it into our free body diagram, right? So let's go over here. Here's our lawnmower. So we've got a 40-kilogram lawnmower. So gravity is going to pull it down. 40 times 9.8 is 392. Roy is pushing down vertically with 68.9 newtons. He's pushing horizontally with 57.9 newtons. There's got to be a normal force that prevents the lawnmower from moving down through the ground. It's got to be big enough to cancel both of these, right? So that gives you 460.9, I think. Yeah, or yeah, 460.9. All right, and then there's friction of some sort. So let's take a quick second and figure out what kind. So our force of static friction max, remember static friction is going to try to prevent the motion. So that's coefficient of static friction times our normal force. Coefficient is 0. Whoa, why does it keep doing that? It hates me, clearly. The coefficient of friction is 0.6. Our normal force is 460.9. Probably don't even need to do the math to realize it's not going to work, but if you multiply that, you end up getting 276.6. Is that right? I just can't read my own writing. 0.6 times 460.9, 276.5 newtons. All right, and in order to prevent the motion, we only need to cancel out this 57. So it looks like that's going to work. So this is static friction, negative 57.9 newtons, and there's your drawing. All right, now, again, technically speaking, if this was the AP test, what you would do is your free body diagram would have your normal force, it would have your static friction, it would have your gravity, and it would have the force of Roy instead of the components. Okay, but for problem solving, you really got to think in terms of components. Okay, so what we just discovered then is that the lawnmower does not move. Well, so what's the minimum force he would need to get it moving? All right, so this is new. Nothing new concept-wise, but definitely new in terms of problem solving. All right, so let's draw our lawnmower again. So here's the lawnmower. It's still 40 kilograms. All right, and our goal is we want to get this thing moving, right? So Roy's going to push still at dropped my pen. So Roy is still going to push at that same angle. Force of Roy. This is still 50 degrees. So there's going to be a horizontal component and a vertical component, right? But since I don't know Roy's force, I can't find those components. But what I'm going to do is I'm going to write expressions for them. So the force of Roy in the x direction is the force of Roy times the cosine of 50. And the force of Roy in the y direction is going to be negative force of Roy times the sine of 50, right? Okay, so that is going to be very helpful because now I'm going to go over here and put it on my drawing. So here's what we know. We know that Roy's horizontal force that's going to try to get this thing moving is Roy's force times the cosine of 50, which is 0.643 times the force of Roy. Okay? Roy is also pushing vertically with a force of negative force of Roy times the sine of 50, which gives you, oh, darn it, I didn't write it down. So just grab the calculator and find the sine of 50. Sine of 50. So you get 0.766, negative 0.766 f. Okay? All right, let's see. So what else? There's gravity pulling this thing down, right? The force of gravity is negative 392 newtons. There's got to be a normal force preventing the motion, and that normal force needs to be big enough to cancel both of these. And so that's going to give you 392 plus 0.766 force of Roy. I just realized I forgot my R here on Roy's force there. All right, and then there's friction trying to prevent the motion, right? And the friction that's trying to prevent the motion is static friction. And our static friction is our coefficient of static friction, which was 0.6 times our normal force. So our static friction is 0.6 times our normal force, which I don't quite have enough room to write. We're going to make it work. 392 plus 0.766 FR. All right, so in order to get this thing to move, here's what we need. We need our net force greater than 0. In simple words, we need Roy's horizontal force to be bigger than or equal to our force of static friction max. I realized I probably could have put max over here, right? Since that's really what we're doing. We got to overcome the maximum force of static friction. All right, so now it's algebra, right? We've got this 0.643 times the force of Roy. It's got to be greater than or equal to 0.6 times 392 plus 0.766 FR. So let's see, we're going to distribute. Or I guess you could divide by 0.6. I've already done this, so I guess we'll finish this train of thought. So what's that give you? It gives you 235.2 plus 0.46 force of Roy. So now subtract and you get 0.183 force of Roy. Has to be bigger than 235.2. So divide both sides, and the force of Roy has got to be bigger than 1,285 newtons. Okay. What I just did here is huge, this chapter, where you need to write unknown forces. And you sort of get this snowball of variables, right? Because these two guys were written in terms of the force of Roy. Once we had that, that meant that the normal force was written in terms of the force of Roy, and that meant that the force of static friction is written in terms of the force of Roy. All right? There will be times when you won't know the angle. And so up here, you'll have your force times the cosine of theta, and you've got to just leave theta in there and go through the whole problem and solve it. Okay. So these free body diagrams are huge, hugely important. All right. That is it for this one. This one, you really just got to dive into trying the problems, okay?